Measuring potential difference and short time interval. By the end of this lesson, you should be able to measure potential difference using the C.R.O. Measure short time interval using the C.R.O. Solve problems based on the C.R.O. display. What is the student measuring? What measuring instrument is he using? Can he use any other instrument to take the same readings? How would you determine the time between two heartbeats? The time between two heartbeats can be measured by measuring the time between several heartbeats, for instance, 21 heartbeats. Therefore, the time interval, or time between two heartbeats, can be calculated by dividing the time taken by 20. Is there any other way to measure the time between two heartbeats? A cathode ray oscilloscope, C.R.O., is used to display a graph of voltage against time. Voltage is plotted on the vertical or y-axis, and time is plotted on the horizontal or x-axis. The screen of the C.R.O. normally has 8 divisions on the vertical axis and 10 to 12 divisions on the horizontal axis. Click on the switch to switch on the C.R.O. Notice that the time base is off. Adjust the X shift and Y shift knobs so that the green dot will be at the center of the screen or at the origin. Why do we need to have the green dot initially at the origin? We need to set the green dot to the origin so as to avoid zero error. Zero error is the error which is due to non-zero reading when the actual reading should be 0. Y gain is set to 1 volt per division, which means that on the y-axis, 1 division represents 1 volt. Time base is set to 0.1 second per division. This means that on the x-axis, 1 division represents 0.1 second. The Y gain and the time base knobs of the C.R.O. can be used to change the vertical or horizontal scales of the voltage against time graph. What does the voltmeter measure? The voltmeter measures the potential difference between points A and B. What is the potential difference between points A and B? The potential difference between points A and B is 3 volts. Switch on the C.R.O. Notice that the time base is off and the green dot is not at the origin. What is the appropriate step that should be taken next? The green dot has to be adjusted to the origin first. Click on the appropriate knobs to set the dot at the origin. What is the Y gain set at? What does the selected value mean? The Y gain is set at 1 volt per division. This means that each division on the vertical axis represents 1 volt. The C.R.O. is connected across points A and B. What happens to the green dot? The green dot is shifted 3 divisions upwards from the origin. What does this indicate? The Y gain is set at 1 volt per division. The green dot is shifted 3 divisions upwards. The potential difference across points A and B is calculated by multiplying the selected value of Y gain to the number of vertical divisions from the horizontal axis. Thus, the potential difference across points A and B is 3 volts. Now turn the time base on. What can you say about the waveform seen on the screen? A green horizontal line is seen across the screen. What may happen to the horizontal line if the connection to points A and B is reversed? The horizontal line is shifted 3 divisions downwards from the origin. The DC power supply is now replaced by an AC power supply. The time base is set to on. What can you say about the waveform seen on the screen? A sinusoidal waveform is seen. What is the amplitude of the waveform displayed? The amplitude of the waveform is 3 divisions, which is equivalent to the selected value of Y gain multiplied with the number of vertical divisions from the horizontal axis. This amplitude is equal to the maximum voltage of the AC power supply. The maximum voltage is known as the peak voltage, VP. What may happen to the waveform if the connection to points A and B is reversed? A sinusoidal waveform is still seen. Turn the time base off. What can you say about the waveform displayed on the screen? A vertical line is seen on the screen. What can you say about the length of the line? What does the length of the line indicate? The length of the line is 6 divisions. This is equivalent to twice the amplitude or twice the peak voltage. Click on the switch to switch on the C.R.O. The pulses produced by the claps can be traced by the C.R.O. How much time does each horizontal division represent? The time base knob is set at 50 milliseconds per division. Thus, one division represents 0.05 seconds. How many divisions are there between two consecutive claps? The distance between two consecutive claps is 2 divisions. Determine the time interval between two consecutive claps. Since one division on the horizontal axis represents 0.05 seconds, thus the time interval between two claps can be calculated by multiplying the selected value of the time base to the number of horizontal divisions for one complete cycle. Thus, the time interval between two claps is 0.1 seconds. The waveform of the alternating power supply traced by the C.R.O. is as shown. At what value is the Y gain of the C.R.O. set? At what value is the time base of the C.R.O. set? The Y gain of the C.R.O. is set at 2 volts per division. The time base of the C.R.O. is set at 5 milliseconds per division. What is the amplitude of the waveform traced? What is the potential difference of the AC power supply? The amplitude of the waveform is 4 divisions. The potential difference of the AC supply, V, can be calculated by multiplying the selected value of Y gain to the number of vertical divisions from the horizontal axis. Thus, the potential difference of the AC supply is 8 volts. What is the distance between two peaks? What does this distance indicate? What is the frequency of the power supply? The distance between two peaks is 5 divisions. The distance between two peaks represents the time interval between two pulses. This distance is equivalent to the period of the waveform. Thus, the period of the waveform can be calculated by multiplying the selected value of the time base to the number of horizontal divisions for one complete cycle. Thus, the period of the waveform is 0.025 seconds. Frequency is the reciprocal of period. Thus, the frequency of the waveform is 40 Hz. Click on the switch to switch on the C.R.O. Drag and drop the different power supply voltages. Click on the Y gain and the time base knob to vary the vertical and horizontal scales to get a good display of the waveform. What can you say about the graph produced? Click on the correct answer. A C.R.O. cannot measure Click on the correct answer. A C.R.O. shows a trace of an AC voltage with the time base adjusted at 10 milliseconds per division. What is the frequency of the AC power supply? Click on the correct answer. In what way is a C.R.O. a better measuring instrument? Click on the correct answer. A sonar signal is used to measure the depth of the sea, with time base set at 50 milliseconds per division. The send and return signal was traced on the C.R.O. screen. If the speed of sonar signal in seawater is 1,200 milliseconds, what is the depth of the sea? Click on the correct answer. An AC voltage is connected to the C.R.O. The Y gain is set at 3 volts per division. Determine the peak voltage. The value of the alternating voltage varies all the time. The average value for one complete cycle of an alternating voltage is 0. For calculations involving alternating voltage, the root-mean-square RMS value is used. The root-mean-square RMS value is the effective value of an alternating voltage or current that has the same heating effect on a resistance when a steady voltage or current is used. The circuit setup consists of 1. A C.R.O. 2. A 3.8 volt bulb. 3. A two-way switch. 4. A rheostat. 5. 4 volt AC supply, and 6. 4.5 volt DC supply. What is the Y gain set at? Mouse over the knob to take the reading. The Y gain is set at 1 volt per division. Flip the two-way switch to terminal M to complete the circuit with the 4 volt AC supply. What happens to the bulb? What do you see on the C.R.O. screen? The bulb lights up. A sinusoidal waveform is seen on the screen. What is the peak voltage as displayed on the screen? The Y gain is set at 1 volt per division. The peak voltage of the waveform is represented by the amplitude of the waveform, which is 4 divisions. The peak voltage can be calculated by multiplying the selected value of the Y gain to the number of vertical divisions from the horizontal axis. Thus, the peak voltage is 4 volts. Flip the switch to terminal N to complete the circuit with the 4.5 volt DC supply. What can you say about the brightness of the bulb? What can you say about the display on the C.R.O. screen? The bulb is dimmer compared to when the alternating voltage supply was used. A straight horizontal line is seen on the C.R.O. screen. Move the slider of the rheostat to vary its resistance, and hence the current in the circuit, until the brightness of the bulb is the same as the one when the alternating voltage supply is used. What is the value of the direct voltage supply when the brightness of the bulb in the two situations is the same? When the brightness of the bulb in the two situations is the same, the C.R.O. shows the horizontal line position to be at 2.8 divisions from the x-axis. The direct voltage supply can be calculated by multiplying the selected value of the Y gain to the number of vertical divisions from the horizontal axis. Thus, the direct voltage supply is 2.8 volts. What can you say about the brightness of the bulbs and the values of the alternating and direct voltage supplies? The brightness of the bulb is the same, even though the values of the alternating and direct voltage supplies are different. Why? The heating effect produced by the two voltage supplies is the same, thus giving the same brightness of the bulb. The value of the effective alternating voltage supply that has the same effect as direct voltage supply is called the root-mean square, RMS voltage, VRMS. The effective alternating voltage, VRMS, is less than the peak value, VP, of the alternating voltage supply. How are these two voltages related? Direct voltage can be calculated by multiplying the reciprocal of square root 2 to the peak voltage. Since the direct voltage is equal to the root-mean square voltage, therefore the root-mean square voltage is equal to the peak voltage divided by square root 2. Similarly, the relationship between the maximum or peak value of the alternating current, IP, and the root-mean square value of the alternating current, IRMS, is given by the root-mean square value of the alternating current is equal to the peak value of the alternating current divided by square root 2. Given that the peak value of an alternating current is 3 amperes and the peak value of an alternating voltage is 5 volts, what are the root-mean square values of the alternating current and the alternating voltage? The root-mean square value of the alternating current is equal to the peak value of the alternating current divided by square root 2. Therefore, the root-mean square value of the alternating current is 2.12 amperes. The root-mean square voltage is equal to the peak voltage divided by square root 2. Thus, the value of the root-mean square voltage is 3.54 volts. The value of the alternating voltage varies all the time. In this lesson, we learned that the C.R.O. can be used to measure 1. Potential difference of a DC and AC supply. 2. Short time intervals. Potential difference equals the selected value of the Y gain multiplied by the number of vertical divisions from the horizontal axis. Time interval equals the selected value of the time base multiplied by number of horizontal divisions for one complete cycle.